Hello. So thank you for joining us. This is already the last talk of the conference. So to end in a good, with a good presentation, let's do more crypto. So first of all, I'm Sylvain. I'm a security researcher at Kudelski Security. I mainly work on applied cryptography topics. I used to do hardware attacks, and I'm occasionally a bad CTF player, but I would be happy to play with you just after this talk to the contest.
My name is Sletterink. I'm a security consultant, freelance, and I have a lot of interest in crypto. So sometimes I get nice crypto assignments, and that's where this all comes from.
So first, how this project started. So one of my colleagues came to me with a USB stick containing a vault encrypted with a SanDisk secure access software. And he told me, okay, is it possible to crack this vault to recover the data? So I started my research. Meanwhile, he was able to find the password. So basically on a post-it. So it could have been end of the story. Obviously it's not. So I will explain you why. So I didn't know SanDisk secure access software at that time. It's a piece of software you find by default on SanDisk SSD or USB stick, and it's quite convenient. You launch the binary, and if you enter the correct password, you have access to the vault. You can copy your data, remove your data. It's really something convenient and perfectly normal so far. But one thing was interesting was that when I've been to the settings, you could see that you could upgrade the software and then use AES, up to 1024 bits. So AES 1024 does not exist. It's not standardized. At least it exists because it's implemented in the solution, but it's not standardized. So it started to interest me, what was implemented in this solution. So I dig a bit deeper, and I figure out that this solution is developed by ENC Security, and they had a really strong security claim on their website. They say that they use ultimate encryption using 1024 AES keys, military grade. And then when I hear military grade for a civilian solution, I always think about these tweets. So then I definitely wanted to know which algorithm was in this solution. So joke apart, this was an interesting project because ENC developed this software as a general solution, and it's used by Lexar, Sony, and Western Digital as well by default on their product to provide data encryption. But at that time, it was not supported by Hashcat nor John the Ripper for password brute force. So my colleague basically could not brute force the password. It was you had to create the plugin for that. And obviously, I wanted to know if I'm able to brute force AES 1024. So I started the reverse. It's a P32-bit binary. It was packed with UPX, so I could easily unpack it with a P Explorer. There were no further debug protection. It was written in C++, compiled with Visual Studio, and it uses Qt for the graphic user interface and OpenSSL for crypto. There was one thing which was a bit annoying to me. It was that if you execute the binary outside of the key, it will tell you, okay, you're not allowed to do that. So since I didn't have any, for example, on the left, it's a Sony solution. So I started in the binary to look for the message, and I found a branch. Just before the message, I found a branch. I blindly patched this instruction, I changed it, and then the binary would execute perfectly fine on my computer. So it was quite convenient. It reminded me good memories of cracking, easy. So it was okay. One thing I massively use for this project is GDRA function ID. It's really convenient when you have an open source library. You create signature of this library, You apply the signature on your the binary you're reversing, and then, for example, it recovers a lot of cryptography function, a lot of graphic user interface function as well in the binary, and it really speed up the reverse. Then I started the dynamic reverse, so I use process monitor, and I looked at how it reacts when I enter a wrong password. And in fact, only one file was read. It was filesystem.dat, and the password, it means that the password is compared with something inside this file. So this was already a good path to follow in my reverse to see how the password is checked. If we just step back a bit now, we are trying to reverse a password hashing algorithm. So basically, we want to derive an encryption key from a password, and we'll then use this key to encrypt data. So usually we use unique and random salt to avoid pre-computed, so dictionary or rainbow table attack. We have a parameter called iteration number, which allow you to adapt how slow a brute forcer will be to brute force your password. And nowadays we use this algorithm for that, so PBKDF2, which stands for password-based key derivation function 2. Balloon hashing is not well known, but it's recommended by NIST, Scrypt, and we have also Argon 2, which is a more modern algorithm. It's a winner of the password hashing competition. So if you are interested to do more into this topic, I really recommend you reading the literature on password hashing competition. It's really interesting. But for today, I will just stick to PBKDF2. The construction is quite simple. You input the password as a key. You input the salt concatenated with the constant 1, and you iterate the hashmark function C times. So C is the number of iteration in this case, and you obtain a key. So it's quite simple. The only problem is, okay, I cannot create a key which is larger than the hashmark output. So how I can create, for example, a 1024-bit key with this construction? And this was the problem of PBKDF1, and it was so PBKDF2 integrate this option. So basically, you run the algorithm first with the constant 1. You say it's my first key. Then you run again the same algorithm, but with the constant 2 concatenated with the same salt. You obtain the second key, and so on. And at the end, you concatenate all the keys you obtained, all the keys you obtain, and you have your key. For example, if you want 1024-bit key, you iterate 8 times this algorithm, and you will have your key. So it's perfectly fine so far. So I started to reverse this function. So I figured out that the number of iteration was hard-coded, and it was 1000. And then I had this loop with this hash function, which was not identified by Ghidra function ID. So I reversed a bit more the algorithm, and I figure out that the solution implements this. So it looks like PBKDF2, but instead of using hashmark, they use MD5, and otherwise it was almost the same. But one thing I struggled in the reverse for one thing, it was how the salt was generated. So I reversed the code, and I found a string which looks random, but since it's in the code, obviously it's not unique. And in fact, it was the salt in the code. And it was even worse because it was shared among all vendors. So Sony, Lexa, Western Digital, and SanDisk. So it was the first problem I found, and it's not really good because you can have a pre-computed attack. You can create dictionary and so on. And also, a second less important problem is that the number of iteration is a bit low for nowadays standard. 1000 was good for the beginning when PBKDF2 was out. But now, for example, OWASP recommends 310,000 iteration for PBKDF2 hashmark 256. But if we think a bit more, there is a construction problem with this function. In blue, you can see that all the computation does not depend on the salt on the constant. So you can compute once this part, and just reuse it for the next step. So it means that you have to compute this part only once. But even though you can create a dictionary of this part, and it means that even if the salt would have been random and unique, you can still compute this part and XOR it with the salt, and that works exactly the same. So even if it was close to PBKDF2, it does not achieve the same security level at all. And basically, the difference between generating 128-bit compared to a 1024-bit key is simply a XOR, because you just keep this value in memory and you apply it. And you can again do a dictionary attack. So it was really a bad design. So this was for the key generation. And now let's see how the password is verified to be correct. So as I explained before, it uses a value store in filesystem.dat. So it's a magic value, which is decrypted. And if the value is D2C3B4A1, then the password is considered to be correct. So I needed to figure out, okay, what is the encryption algorithm? It was not easy to me, because I'm not a good reverser, but it was not identified by Ghidra ID function. It was SSC instruction. Decompilation was not working good on that. But I knew at the end it used OpenSSL. So I opened OpenSSL code, and at some point I found a Perl script in OpenSSL which generates assembly, which looked exactly the same as the instruction I had in my code. And in fact, it was just AES. So for the AES 128 mode option, it was simply AES in counter mode, so standard. So then I think, okay, for AES 256, it's AES 256 in counter mode, no problem. But in fact, it was not. It was 2 iterations of AES 128, but the second key, which was generated by the key generation function, the first half is XOR with the nonce before the encryption. Otherwise, if you XOR two times the same thing, you will have nothing, so it won't work. And then I could figure out how AES 512 and AES 1024 mode worked. It was just 4 and 8 iteration of AES 128, with each time the key XOR with the nonce. So the difference between AES 128 and AES 1024 is just the number of iteration of AES. And in addition, the software just used half of the key bits generated. So already all the key bits were not used for this part. And at the end, obviously, if you use a weak password, it won't help you to have such a function. The level of security will be linked to the level of security of your password. So at this point of the project, I got anything I needed to implement a plugin for John the Ripper. So I create a script which will extract the data and format it to John the Ripper. As you may notice, the magic word is 32 bits, so you may have false positive after each to the power 32 candidates. But you can filter out this false positive with the second word, which is the number of volts on the disk encrypted. And so now it is integrated in the main repository of John the Ripper. So now everybody is able to brute force AES 1024. You can just use it. Just let's see how it runs. So it's quite easy. You input the hash, the file with the data extracted from the vault. It will run, and if your password is in your password list, or if it's brute forced, it will be recovered. For this one, it took only 2 seconds to be brute forced, because it was in the password list. And John the Ripper, on a single core, was able to test 7,300 passwords per second, which can be compared with PBKDF2 with 310,000 iteration. So the same password is found, but after 2 minutes. And John the Ripper is able just to test 30 passwords per second, which is really, really slow. So it will really slow down a brute force of this algorithm. So then I had the John the Ripper plugin to crack password, but one thing is missing is, okay, as soon as the key is derived, how the file are encrypted in the solution. So in fact, it's quite standard to have a file containing file encryption key, which are encrypted with the derived key, because if the user changes password, you don't want to re-encrypt all the vault. So there are a file encryption key which were encrypted with this derived key. And I needed, and then this file were used to encrypt those files individually. So I needed to know how it was encrypted. And I assume it uses the same encryption algorithm I presented before. And it was the case for AES 128 option. It was AES in CTR mode. So I was like, okay, it's the same for AES 256. But I was surprised it didn't work. It's not exactly the same. Now the key, the file encryption key, is completely XORed with the nonce and the counter. So I was like, okay, why not? So then I was like, okay, for AES 512, it should be 4 iterations of AES 128. And in fact, no, it was not working like that. It's only 2 iterations, but they use only the fourth key for AES 512, and for AES 1024, the 8th key. So it was only 2 iterations of AES 128. I reverse also the file format of the encrypted file. There is nothing really surprising. The IV is at the beginning of the file, that's the version of the software. A parameter for the AES key len, so 4 means AES 1024. Then the file name len, the file name is encrypted. Then we have 0 and offset. At offset 200, we have the start of the file content. So from this, first, it's a CTR design. Even if we have 2 iterations, it's a CTR design. So if you XOR something to the encrypted file, when you decrypt it, you will have exactly the same modification without any notice. So it's a problem. And also, since there is 2 iterations, you have at most 256 bits of security level, because you will have to brute force the key and the second key, which is XOR with the IV. So yeah, it's 256 bits of security at most. But if we do some math, so sorry, it's a bit late for that, but it will be quick. Assume we have 2 plain texts which are 0. We can write the encryption equation. So the first ciphertext is equal to the encryption of the first IV, XOR with the encryption of the first IV, XORed with the last key, and exactly the same for the second ciphertext. The plain texts are not involved because we assume they are 0. And then if we decrypt each part and we XOR them together, we'll have on the left this equation, which depends only on K1, the first key. And on the right part, we have the XOR of the 2 IVs, which are known. So it means we can theoretically brute force the left part on 128 bits until we figure out we have the value we expect on the right. So it reduces the security to even 128 bits. But wait, I assume I have plain text equals 0. But in fact, it is the case, because if you remember well, in the file format, I have lots of 0 which are encrypted in between the file name and the file content. So this reduction applies to this solution. So it's at most 128-bit security. So it's all for me. I disclose all the findings to ENC security. So they acknowledge, so it was May last year. They acknowledge the vulnerabilities. The vulnerabilities were disclosed to the manufacturer as well. I got a first meeting with ENC security to agree on a deadline to patch the problem. I received 2 CVE, one for the key derivation problem, one for the file malleability problem. Then we had more meeting with ENC security, and they figure out that the key derivation function is used in other Western digital applications. So we extend a bit the deadline. And finally, in December, secure access software, a new version of secure access software, is released, and it's now available. And also, I integrate the new key derivation function into John the Ripper, so you can brute force the new AES 1024-bit version with John the Ripper as well. So that's it for me, and now I will let Boy explain his side of the story. So,
thank you, Sylvain. Yeah. So, as an overview, I'm going to talk about our side of the story from ENC point of view, some events that we had, challenges, choices that we made, and how we got to those choices. At first, I'm going to give you a little bit of background. The company has been around since 2009, so it's been there for quite a while. Currently, it's based mostly in the Netherlands. As you can hear, I'm from the Netherlands. We actually have millions of people using our software, but that's mostly because we have made OEM versions that are delivered on USB sticks. And those OEM versions, they come from SanDisk, Sony, and Lexar. And SanDisk has been bought by Western Digital, so that's effectively Western Digital. And they're actually the only paying customer, big customer that we have right now. And Sony and Lexar are not paying for updates or anything anymore. However, Sony did respond to the requests, and they said, yeah, we would like to have an update, when you've got it. We never heard anything from Lexar, even though we tried. On the other hand, we've been in very close cooperation with Western Digital to get this stuff fixed. So, actually, for me, from my side of the story, I want to go slightly more back than Sylvain, in the sense that I was first involved with ENC around April 2021, because they wanted to have a security assessment of the software. It was a fairly simple assessment, and I found some stuff in it. I reported it, and they said, thank you, we're going to fix it. And 2 months later, I suddenly got a call. Yeah. There's this guy, Sylvain. He said he found stuff in our software. Is this real? Do you have time to look at that? I said, well, sure. So, yeah, then all of the events in the timeline here, they happened. So the first thing that they asked me was, okay, so is this report for real? Because you've got a nice looking report, made by a guy who you don't know, and he's claiming all kinds of things. Some of the things were actually not very surprising because they were basically the same that I found. I used a lot simpler approach, by the way. I did not do any reverse engineering. I asked some questions and got to some conclusions. And actually the ciphertext malleability I did try for myself because it's fairly simple with a hex editor, if you know what the plain text is already. So what the first thing that I did is I Googled for Sylvain because I didn't know him. And then, okay, so looks serious. Looks like, you know, he's doing this kind of stuff. That makes sense. I looked at the report. It looked very well written. It is also specific to our product. So it's not like a random scan or source code or binary analysis with some tool and then auto-generate a report or anything like that. So that's a good indicator. It confirmed the vulnerabilities that I already found or, made probable by just asking questions. And also his terminology in the report and the evidence he presented was really convincing. So I was like, okay, yeah, sorry to say, but this is for real. You've got to take this serious. So, yeah. All right. So they asked me, can you then please help us to fix these issues? So I did. I helped fix the issues. Right now, I'm not that actively involved with ENC anymore. I'm still there for questions about encryption mostly and some other advice. But in between, I was the technical lead for implementing the changes. Okay, so this sounds easy, right? Just use a new key derivation function and just use something else to fix the ciphertext malleability. Because these things are not new problems and there are proven solutions to this. So it sounds easy. And it always sounds easy if you don't have to do it yourself. You probably once or twice had a situation where your manager thought that something would take only an hour. Yeah. So the company was actually in sort of like a maintenance mode. So before there has been a lot of development in the software, but right now the company is actually in maintenance mode, which meant only small changes, bug fixes, not very much development. So that also included a small team. Yeah, and suddenly we had to do more things, which made it hard. We now had to increase our team size, make a plan, come up with a design. We had to take a look at the bugs and set priorities for fixing them. And we also had to work more closely with Western Digital than we did before. So this upscaling thing, yeah, imagine that you need new programmers in summer holiday. And you want them actually next week, if possible. That was hard. So we did manage to find some people, including myself. I'm not actively programming anymore, but I can look at the code, which is really helpful because I also found some minor bugs. And I can review other people's work. But I was working part-time for this company because as a freelancer, I sometimes have different assignments at the same time. And the other hands that we also found were also part-time. So yeah, we had more people, but we didn't have that much extra capacity. Then the next step we took really was some triage. How bad are these findings really? How bad are they impacting our customers? Now for the key derivation function, that is actually quite easy. It's not good at all. It's a bad thing. So we want to have that fixed as soon as possible. And we looked at the ciphertext malleability. And if you look at that, I'm going to explain that later, but it is not as bad as the key derivation issue. So we were going to do that later and have a staged approach. Then we had to make a choice on what kind of key derivation function we were going to use. And there are several options, and Sylvain already mentioned them. And we looked at things like performance, security, the time and effort needed to implement the stuff, but also compatibility. We had to find a way to for the new software to open the old vaults. We also had to take usability into account, and we really wanted to make sure that people were using the new version and have the new KDF in place so that they were not using it in a compatibility mode or something like that. And in the end, we just made it not possible because if you open an old vault with the new software, it will upgrade it immediately, right? Because it can just use the password that you just entered. It knows it's an old style vault. It can open it, and then it will just write new headers so that you now have a more secure vault. We also had several options, and we looked at that. And in the end, we decided to use PBKDF2 SHA-256 simply because it was available in OpenSSL, which we were already using. The other alternatives, I personally like them better in the sense that they're also memory hard. So you can't really easily accelerate them with a graphics card or with FPGAs or ASICs. With PBKDF2, that is possible. But yeah, due to time constraints, we decided to go with PBKDF2. So we had some more challenges when we finally decided on that. Well, finally, it didn't take like a long time, but it took some time. So as I mentioned before, we had limited team capacity, but we're also a new team. So we had to get to know each other. We had to tune our schedules because if we all also have other stuff to do, you need to tune your schedules. And this was actually, if you look at our extended team, that also included people from Western Digital. because we also had to meet with them on at least a weekly basis and sometimes even more often. And some of the people from Western Digital were in India and other people were in the US. So you can see that that might pose a challenge. And at some point, for example, I found out that for us, like 4 o'clock in the afternoon was a good time. And then I found out, but for the guys in India, that's like 9 o'clock at night. So, you know, we rescheduled stuff to early in the morning, which was fine as long as we did not have one of their American colleagues in the call as well. Then there were holidays and festivities that would take extra time. People getting sick, not surprising in that period of time. I mean, it was 2021. And it took some more time than we thought to prepare statements and documentation for the user, etc. Those are all things that I think we underestimated. Then there were some other challenges that we faced. It turned out that Apple came out with a new macOS version, Monterey, and that broke our code. So we had to make a fix for that. That wasn't really that easy in the beginning. In the end, it worked out fine, I think. And then also Google decided to upgrade their security requirements for the Play Store. So there was an API version update, and you just could not publish new versions of software if you did not use that new API version. That broke our code. So yeah, that was kind of annoying. We also had to fight scope creep, simply because there were also some more bug fixes outstanding and feature requests. And yeah, when you're going to make a new release soon, why not include them? Well, because it makes it harder to do it soon. Yeah, the Vault upgrade approach I just discussed. So are we going to make it voluntary for people so that we just present them with a pop-up saying like, you can upgrade your Vault. Would you like to do this? And we decided against that. So we just always upgrade the Vault just to make sure that people do it. We had some limitations in our testing capability, and that is on the desktop side for the product that you've seen. There was also an issue because we didn't have dedicated testers at the time. But there's some more complexity here because we did not have access to all of the code because Western Digital developed mobile applications and they tested that part. So that, you know, you can probably imagine that some of the testing, you find a problem and then you don't know, is it in my part or is it in your part? So that was a bit hard at times. And to give you an indication, here you can see, the Data Vault software is basically, there is Data Vault 6 software, which is, the Data Vault is the name of the software that ENC builds under their own name, right? So we have Data Vault 6, which is the old version, and Data Vault 7, which is the new version that if you buy it nowadays or you get the trial version, you get Data Vault 7. And it's, honestly, that's mostly just user interface changes, but based on the old user interface, there is a different repository, which actually you can generate different other versions of. So Data Vault Lite is the Sony version. Secure Access is the old version used by SanDisk, and they wanted to have it renamed to Private Access. So Private Access is the new version. And then there's the Vault API, and the Vault API is a thing we produce to be included in Android and iOS applications. And then obviously Western Digital, they have, as far as I know, they have 3 different kinds of apps, and they maintain that part of the code. If you're looking at upgrade paths, you can clearly see that we have obviously those 3 different product lines. And honestly, I forgot to include the mobile applications here. But what we wanted to have is a situation where if someone was still using Secure Access, they can download the new version of the software and immediately from the secure access version go to the latest private access version without having to do complicated stuff, because it is intended for regular users. But we also wanted to make it possible for people to buy our upgraded version, which has AES 256. I'm using air quotes for the reason. And it also has some usability features that are really nice, like you can mount the Vault as a drive or as a folder. But we also wanted people to be able to do an upgrade like this. So you can see that gives you a lot of different test cases that you have to test. While on the subject of testing, that wasn't always that easy. And that's because the software, like Sylvain showed, the software is made to run only on specific hardware. And honestly, that's a bit of a misnomer. You have to run the application from the USB stick or from the iExpand charger. Because if you don't, then it doesn't see that you're using a device that has a license for it, basically. So if you just copy the executable to your hard drive, it doesn't work unless you fix it. And it's easy to buy one of those USB sticks from SanDisk nowadays. And I'm not sure about the iExpand charger, but I got one from the company, so that's easy. But the Sony SSDs, you can't get them anymore. Maybe on eBay or something like that. But I just couldn't get them anymore. One of my colleagues told me he had a prototype, which is basically the same contents as this thing, but without a casing. And then I decided to use something different. I was hacking it like the 20s. So I used an Orange Pi and ran Linux on it. And I used the Gadget kernel module, the G mass storage module, to just fake a USB device with specific vendor and product IDs, and it worked like a charm. Yeah. So then we had a deadline when Sylvain was going to make everything public. And we agreed on a deadline. And then we were not able to make the deadline. That is, we were supposed to get out a fix for at least the key derivation function issue before the deadline, and we were not able to. So yeah, we were actually quite happy that Sylvain was like, okay, I don't want to endanger users, so let's postpone that. By then, the talk for the CCC, I think, was already confirmed. Is that right? Yeah, so we had a much harder deadline. But yeah, finally we went live with the key derivation function fix in December. So yeah, now I'm going to explain a bit about the ciphertext malleability issue. And to do so, I first want to explain to you a bit about how stream ciphers work. I mean, I'm assuming not everyone knows how this stuff works. So basically, you can divide ciphers in two types, block ciphers and stream ciphers, and AES is a block cipher. But block ciphers also have some inconveniences, stream ciphers have some good properties, and there's actually a trick to use AES in what's called counter mode, which means that you use a counter to create a key stream, and this key stream is not predictable by the attacker, but it is predictable by anyone who knows the key. So what you then do is you just XOR the plaintext and the key stream together, and then you get the ciphertext. It's a really simple way of doing this. Now, does anyone in the room know what it says over here? Okay, we're going to see. Because the next thing is, if the attacker knows the plaintext, what could possibly go wrong there? Well, a lot. Because if you decrypt things, if you take the ciphertext and you XOR the same key stream on top of it, then you get the plaintext again. That's one also a very nice feature of counter mode, because for counter mode, encryption and decryption are exactly the same. There's no change in code whatsoever, which gives you very efficient implementation in software and also in hardware. And this plaintext is actually the word test. Okay, but then suppose I want to change that word test. I want to make the first lowercase t a capital T. That's actually quite easy to do, because that's only one bit difference. In ASCII, the difference between upper and lowercase is always the same bit, so it's really easy. So from this angle, I can't really see it all that well, but over here, if you just flip the bit in the ciphertext, the corresponding bit that needs to be changed to make it an uppercase character, on decryption, the plaintext also gets the corresponding bit flipped. You can make single bit manipulations in your ciphertext that give corresponding single bit manipulations in the plaintext. And you can do that for every bit. It's not limited to only one bit. So if an attacker knows the plaintext, that's an obvious problem. Now the good news is often attackers don't know the plaintext. So there are a few conditions for this vulnerability to be used. And the main one is really, where is my pointer? There it is. The adversary always has to know at least something about the plaintext. At least have to know the format. And usually it requires knowing a big chunk of the plaintext. And the other thing is, it requires there it is. It requires to steal the USB stick. You have to have access to the USB stick, then manipulate it, and then put it back in such a way that the victim does not notice that there's something wrong. Because if they notice something's wrong, they might get paranoid and not use the stick anymore. And these conditions actually make it relatively hard to abuse, especially the part where it says that you need to know the plaintext. However, if you do, for example, if someone would have a Windows executable in the vault, and someone else, the attacker, knows exactly what executable it is, the attacker can replace that executable with anything else, any other executable of at most the same size. And by the way, making it smaller is also easy because you just chop off the bytes that you don't need. So it is hard to abuse, but if the conditions are met, it is relatively easy to do. Okay. How to fix it? Well, there's a proven solution for this, which is relatively simple. You just need to generate a message authentication code over the entire contents of the file. It's best to do this on the ciphertext. I'm not going to explain here why, but that's generally accepted. And there are multiple ways to do so. For example, there it is. You can use, instead of R counter mode, you can use Galois counter mode, which also produces GMAC. You can use an HMAC, which is a hash MAC construction. And this will solve the issue completely. And it is actually not even that hard to implement. Okay. But why didn't we do that immediately then? We have two usage modes. One is that you can, the picture you saw, the screenshot you saw with Sylvain, you have a drag and drop interface where you can drop files into the vault and you can drag them out. You can also double click on them and then get them opened, which effectively what it does is it will decrypt it to your hard disk. And then the application has started to handle the file. And if you close it and it has changed, it will actually put the file back into the vault and replace the original completely. That's one way of doing it. that, I guess it is acceptable to do it with the HMAC construct as I just showed. However, we also have a direct access way of using. And you can do that, for example, with the mounting of Vault on the desktop version, on a drive or on a folder. Similarly, the mobile applications, they use the Vault API, and that basically also have random access, direct random access to the files. And they also actually use that. Because what you can do now is you can open a file, but only read a bit, a small bit, or write a small bit of the file, and then close it again. And you only have to encrypt and decrypt the bits that you're reading or writing. Okay. Now, suppose you have a folder with a lot of large video files, several hundred megabytes of video. And many of these video files do contain an icon, right? If the Explorer wants to extract the icon from the file, and you have this MAC construct, this authenticated encryption, because that's another name for it, it will have to do this entire check over the entire contents of the file. So if that's hundreds of megabytes for just a few kilobytes of an icon, that's a lot of work. So this makes it really slow. And similarly, if you change something, even a single byte, if you change even a single byte, then the MAC will have to be recalculated over the entire contents again. So that's expensive. Okay. There are other ways to deal with this. You can do the same thing, but over smaller chunks, over blocks, if you will, which is a good idea. People have been doing this before. However, it does not fit really well into our current design, so it's a lot of work to change it. There are other alternatives that we considered, and at first we thought that's what we're going to do. We're going to use XTS mode, because that's also used by BitLocker and by Lux, and it's well known. And the thing here is, there's still ciphertext malleability, because you can just edit the ciphertext, and if it's decrypted, it will be different. However, it's now restricted that if you make a change, even one bit in a block of ciphertext, then a corresponding full block of the block cipher is going to be completely different. And you can't specifically target individual bits or anything like that. It's basically, you can destroy a block, but you can't manipulate it in a very targeted way. And these blocks are usually, in our case, it's 128 bits, right? Because it's AES. So that's like 16 bytes. Yeah, that sounds nice. But again, this doesn't really work with our code, because our code expects to be able to encrypt and decrypt single bytes. And sure, you can fix this. But the most naive approach is going to be very costly if the program actually accessing the file is reading or writing single bytes. That's going to be really expensive. So you need some kind of a buffering or caching layer on top of the crypto layer. Much more effort than you were hoping for. So effectively, this has not been implemented yet. And it's intended to do this somewhere this year. We also discussed it with Western Digital, and they definitely want to have this fixed too. But there are now also other bugs that we want to have fixed first, because it's, thank you. Yeah, it's a trade-off you have to make. These bugs are affecting most users in most use cases more than this bug. So one last thing, AES 1024. So when I was starting on, when I accepted my first assignment, I started reading the marketing material on the website, and then I read AES 1024. Right. What did I start on? And now that I've talked to people within the company, and some of them have been around for a long time, they told me, well, yeah, we know it doesn't exist. We know it's not a NIST standard. But we had export regulations, so we could only ship AES 128. But we wanted to offer something stronger than that. So we would just do multiple rounds. And how to market this? Well, bigger numbers. People understand bigger numbers. It sounds stronger, especially if you call it military encryption. Yeah. So that's the background of this. Yeah. So our conclusion.
Yeah. So as you have seen, it's really difficult to assess the level of security of a solution. Depends many things. The algorithm used, the size of the key, the number of iterations. So we have to be careful when we announce numbers. And with this talk, I wanted to, because maybe you've seen before in previous talk, sometimes it's difficult to do vulnerability disclosure and sometimes it's badly done. And for this project, it was really nice, a nice collaboration. And it was under really in a good way. We had a lot of meeting, and I'm happy to show you the both sides of this analysis and how it should happen. I think most often, like defensive side should understand the problem from the defensive side, and same way around. So it was really nice in this way.
Yeah, it was a really nice and surprising idea of you if I would join in. So yeah. So
if you have any questions, and you can ask them. We have a few minutes to answer, or you can contact us by this means. So feel free. Thank you.
Thank you very much. If anyone has a question, please raise your hand.
Yes, I took.
So are they still branding military grade 1024, or did they work back to 128 and 256?
It's the marketing material still calls it a military grade encryption, and so the actual implementation is the AES 256 is not AES 256 as designed by NIST. And we also are going to fix that because it's relatively easy to do. And AES 512 and 1024 will be then 2 and 4 rounds of those. And that will also be done at the same time as the ciphertext malleability is addressed. Yeah.
It's not really a question, it's a comment on your last slides, essentially. I wanted to applaud you because in my experience, it's very rare to have such responsible disclosure and have both sides of the story at the same time. So thank you very much.
Thank you.
Thank you.